Okay, so let's wrap up this review paper on enhanced weathering. What are the impacts of what are the impacts, potential unintended consequences, and what are the monitoring requirements? Let's read this impacts a little bit. Deployment of EEW with basalt could have negative effects on the plant, soil, water environment and require monitoring. Anything we do, especially geoengineering, we're trying to correct one problem we created with another technique, and that also could have unintended consequences. So monitoring is very critical. Potential accumulation of trace metals released by weathering of basalt and other potential silicate feedstocks in soil and edible portions of crops has been raised as a possible concern. Oops, I don't know what I'm doing here. As a possible concern of repeated EW practices over time. In other words, as I mentioned in the last podcast, it's nice that you can put crushed rocks on the soils, enhanced weathering, add carbon to soil, make it richer, increase crop yields. But how long can you keep doing that? However, the biogeochemistry of trace metals in plant soil systems is complex, and metal solubility decreases with increased pH, precipitation of secondary minerals, and adsorption onto cation exchange surfaces such as clays and organic matter. So the solubility is an issue there. Additionally, application of crushed basalt can increase soil aggregate formation, potentially reducing solubility of trace metals as well. No marked changes in soil metal concentrations have been observed in many EW field trials, including those running for years and using high loadings of crushed basalt, so that's order 100 tons per hectare. So many years, but what are we talking about when we want to use EW as a part of the solution? Are we going to keep doing it for decades, in which case we don't have the data? These few years of data may not be representative of long-term impact. So monitoring obviously becomes critical, and stopping it should be possible, unlike, let's say, spraying aerosols into the stratosphere. If you stop, then it takes time to wash them out and so on. Same thing here, but at least you can stop putting more rocks into the soils. Scaling EW through carbon credits is another consideration. Voluntary carbon market and government procurement of carbon removals are likely to grow substantially in the future overall. EW could meet an important fraction of this demand while addressing the permanence concern arising from other forms of CDR, such as via land management. However, issues associated with carbon accounting. So essentially, you have many approaches being proposed and tried already. Can EW somehow keep filling the gaps somewhere when the other ones are not meeting their expectations or so? Learning from the existing carbon markets can work. Carbon credits, which are used to offset emissions generated along the value chain of the corporations, need vigorous validation based on cradle-to-grave accounting. We call it life cycle analysis in other contexts. Or half of the 2,000 largest publicly traded companies in the world have made public net zero commitments. In the voluntary carbon market, corporations purchase carbon credits to offset emissions and meet their commitments. Rigorous offsetting claims require cradle-to-grave accounting of all life cycle emissions associated with a CDR deployment and tracking of carbon losses or reversals over large spatial and temporal scales. And so for EW, emissions need to include those from quarrying, grinding, transporting materials, and all carbon losses downstream of the field. So it's not a trivial task, but the charge is to reduce carbon dioxide from the atmosphere. Then cost-benefit analysis and life cycle analysis should be done. A takeaway from the most strident criticisms of early carbon markets is that the voluntary carbon market might be fundamentally flawed might be a fundamentally flawed financing path for practices such as EW that have a range of core benefits, but where precisely quantifying carbon fluxes might be difficult. Carbon accounting at the regional scale rather than field or project level is one of the important steps towards accurate quantification of carbon fluxes, and EW scaling not only needs government support but also strict rules learned from these early employments. So barriers to upscaling EW, I won't go into the details, but basically climate relevant scales have to go to gigatons, and the voluntary carbon market is small compared with the global need for emissions markets as of now. In 2023, for example, 164 million carbon credits were retired at a total market value of $1 billion US. For comparison, global energy emissions reached a record 37.4 billion tons of CO2 equivalent in the same year, and this number keeps going up. CO2 equivalent is good because it also accounts for non-CO2 greenhouse gases. EW credit purchases were a trivial fraction of less than 1% of all carbon credit purchases, and most were from 5 entities that you can look up in the table given there, the link given there. Policy support and public perceptions are always important, so it's important to evaluate which policy mechanism or combinations of mechanisms can be scaled responsibly in different regions with support from communities and agricultural producers, so you can't just go around spraying things. You have to involve the stakeholders, so we'll look at the table in a minute. Policy support, EW will require sustained policy support to achieve climate-relevant scales of CDR, but exactly how the policy tools will look like and who will monitor the policies for their unintended consequences are also important. There is also a need to develop standardization of EW methodologies using data from commercial and publicly funded field trials, which seems obvious, but data sharing and transparency has to be ensured. So here is the table: carbon dioxide removal policies and programs and status in relation to enhanced weathering. There are the jurisdictions, so various countries, and they are either credit purchasing or trading, and practice-based subsidies. And policies and programs include things like green government strategy, CDR purchase pilot price, and incorporation of CDR into UK emissions trading scheme. And there are the timescales out to 2030, already tried during 2023-24 in the US, 26 to 35 in US, California. California is always trying things ahead of the nation, and there is a California effect, which means if something succeeds in California, other states tend to follow suit. UK 2029 onwards, so it's in the plan. And there are others like Canada, Poland, Brazil. This is regulation based. So you can have bottom-up market forces doing something versus top-down regulation controls. Which works best is always a mix rather than one or the other. There are also research and development ideas underway. Australia, European Union, UK, and there are voluntary certification programs underway in the European Union and France. I won't go into the details, but there are various timescales. You can read some of them. US, for example, tried the carbon negative shot, funding to decrease the cost and support commercial scale-up of durable CDR to US 100 per ton across multiple pathways. So one of the ways in which the cost-benefit ratios are measured is to simply go after a particular number for per ton of CO2, how much does it cost to sequester it by whatever method, and that number is somehow considered to be good when it's below 100 or so. Right now it tends to be in multiple hundreds or even higher, and there is additionality assumed, and sequestration timescales are always considered long, and you have to be careful to read the fine prints on those. Regulatory barriers, of course, EW activities must adhere to regulations across the supply chains. Large-scale deployment of EW will require clarification and, in some cases, adjustments of existing regulations to enable access to feedstock, set safe thresholds for application of feedstocks. Essentially, you are doing quarrying already for cement, for various other things. Now we are worried about mining for lithium and other metals and minerals we need. And then there are the rare earths that are a big part of the trade negotiations and so on. And then you're going to add EW quarrying basalts for just crushing them and enhancing weathering, right? Public perceptions and acceptance always matter. Scaling up EW across different regions of the globe needs to address ethical and social issues. Research on perceptions of CDR and EW can help understand when and where controversies might arise and the conditions that public will place upon EW deployment and requirements for governance and responsible innovation. These are standard words, but they are still very critical. In research, people who see EW as interfering with nature are less supportive. So public concern for climate change is high in many countries. Awareness and knowledge of CDR and EW, on the other hand, is low. So CDR is, it's considered a moral hazard because if you start doing carbon drawdown, then people may see it as a way to continue fossil fuel use and not worry about reducing consumption and emissions, right? So time lags in carbon dioxide removal, something to worry about. So there are, how long does it take from spraying or spreading the crushed minerals or crushed rocks onto soil to the entire process to actually lead to carbon drawdown? Will we see it in 1 year, or will it take multiple years? What will be the unintended consequences? So developing empirical constraints on magnitude of cation exchange lags and validating representation of cation exchange and alkalinity breakthrough in reaction transport models using long-term field data from solid and dissolved phases are priorities of future research. So these are kind of details that make me wonder when EW will become a big player, if at all. So it's important to emphasize that carbon removal lags are a fundamental feature of many CDR technologies, including forestry projects, of course, biochar and ocean alkalinity enhancement, and these are not by any means restricted to just EW. Currently, the voluntary markets do not deal effectively with removal lags in any carbon removal sector, and developing sensible strategies. So if you pay for offset this year and that offset happens 10 years later, how do you account for the emissions, or will emissions keep building while these lags play out, and so on? So to conclude, again, briefly, summary and future perspectives. There is growing recognition of the need to avoid overall reliance on a few CDR technologies by diversifying national CDR portfolios to reduce trade-offs and policy costs and to increase sustainability overall, and of course to stay compliant to net zero and global warming targets. EW has the potential to rehabilitate degraded acidified agricultural soils, reduce the climate impacts of agriculture, and bolster rural communities worldwide if it works as it's supposed to. However, gaps in scientific understanding and limited policy and governance frameworks must be addressed for continued effective scaling of EW. In my mind, even after reading the paper and recording these podcasts, it's a question of how can you do EW in reality? Will you keep on doing it on the same fields over and over again, or do you have to look for new fields after some time, and so on? So this review highlights that scientific gaps in technical understandings of the short-term and long-term biogeochemical processes affecting carbon flows and CDR efficiency of EW from soils to the oceans, so cradle to grave. The modeling of these flows across interconnected domains of soils, groundwater, river systems, and coastal oceans, and the impact of an EW deployment on yields and soils must be addressed to progress EW science and employment. So there is a section there that says how employment can be generated as well. Investments in large-scale EW trials offer excellent opportunities to address key scientific questions in some of these targeted priority areas. Rapidly growing commercial investment in EW with agriculture is accelerating deployment at a rate that is arguably ahead of scientific and social understanding, because there are a lot of companies selling EW as offsets or making money by convincing farmers that this will increase their yield, etc. This situation creates notable risks, though. Venture-backed EW companies supplying carbon removal credits to voluntary market registries that are not transparent and robust could undermine public trust in EW. This is very critical. Simply greenwashing can go on for a while before you realize it's all a hoax. Second, if governance and incentive frameworks are not developed at pace with technical understanding, there's considerable risk that EW will not be accepted by key stakeholders regardless of technical rigor. Realizing the potential of EW requires long-term coordinated development of robust technical understanding and responsible frameworks for policy and governance. Continued investments in fundamental EW research and policy is needed to address knowledge gaps and to promote sustainable, responsible long-term growth, which is a very motherhood statement. This is always true. But in the meantime, we have to see how practically the EW deployments that are happening will play out in terms of actual CDR and many other unintended consequences and just reality of additional carbon sequestration. Okay, so even though I keep saying I'll keep it brief, as you know, these long podcasts tend to be these long papers tend to be not so brief, so this is total of over 45 minutes, which is okay. But if you are interested in the details that I skipped, then definitely go back to the paper. It's a very nice paper. It took me a while to read, and incredible number of very useful references as well. Okay, so I'll leave it here for you to follow up more if you want.